just going to make a very short video because I had a little idea walking back from lunch about question 39. I have a sort of an invariant that might be rather simpler to work with than the one I was working with. And so I want to outline that. Now just to quickly explore whether it actually does do the job for me in a nice way. So I'm going to assume that well, perhaps I'll just quickly say once again what the problem is, but I'm not going to do a whole lot of explanation of where this idea comes from, because that comes from in the previous video in this series. But the game is that you have some points in a grid, and what you're allowed to do at any one step is take a point that you've got. If that neighbouring point and that neighbouring point are both free, you can get rid of this point and replace it by 2 points in those two places. And what I came up with was a quantity that increases by a certain amount as you do that. But now it occurs to me that that was maybe slightly silly, and maybe what I should do is just try to come up with an invariant. And then the obvious invariant is going to be one that attaches values to each position and then sums up those values over all the occupied points. And if you want it to be an invariant, then you're going to need that those two, well, it's not going to be absolutely essential, but you need that the sum of those two values is equal to this value. And the most obvious way of achieving that, although not necessarily quite the only way of achieving that, would be to take these to be half this value. Perhaps it's worth exploring other possibilities in a moment, but so that would mean that perhaps we give a value 1 to the point 0, 0, and then a half to those two values and a quarter to those three values, and so on, and then we sum up. So so each time I replace a chip by 2 chips in the unoccupied squares up just above it and just to the right of it, I'll replace this quarter by 2 lots of an eighth or something, so nothing, the sum doesn't change. So that absolutely is an invariant. If I start with all these 6 things occupied, then the value taken is 1 plus 1 plus 3/4, so that's 2 3/4. And so if I could show that the sum of all the rest was less than 2 3/4, then I'd be in very good shape, because that would demonstrate that I couldn't end up with a disjoint bunch of chips after operations of this kind that all lived outside those 6 points. So what's the sum I need? So I've got 1 plus twice a half plus 3/4. So I want 4 over 8 plus 5 over 16 plus 6 over 32 plus 7 over 64, etc., etc., is less than 2 3/4. That would be really nice. And the way I know of thinking about this is that it's summation by parts. So we have an 8 plus an 8 plus an 8 plus an 8, and then we have a 16th plus a 16th plus a 16th plus a 16th plus a 16th, and then we have 1 over 32 plus 1 over 32. So this way we're just counting, we're summing up all the rows first, and we're summing up each row and then summing up all the totals. But if we then do it instead by column, what do we get? We get an 8th plus a 16th, that makes a quarter. That makes a quarter. That makes a quarter. And that one makes a quarter. But now it's going to start dropping, plus an 8th, plus a 16th, plus etc., which is 1 plus something that's going to be, it equals 5 over 4. which is definitely a lot less than 2 3/4. And so there we have an extremely quick proof that this idea has worked in order to demonstrate the first part. But so the first part, that you can't get all 6 of these things out. What about if we start with a 1 only in the bottom left-hand corner? That was the other part of the problem. So now it's not so good because I've got 1, and 1 is not bigger than 2 3/4, anything like. And because it's an invariant, I'm not going to make things much bigger. But we can at least. But on the other hand, it's not clear that I can. So there may be things I can say that will prove that I've actually got to do quite a lot of fairly serious work in order to get to get rid of things. So this 1, I'm going to write. Just want to see whether this invariant has got a chance of making things work nicely. So here we have a half, a half. What is the... so what I want to show is somehow that I can't fill up anything like 2 3/4 worth of the area that's outside these 6 points. But how would that work? In fact, what on earth am I even saying? Because it's invariant. So when I pull these things out, it'll fill up 1. And there aren't things that I am forced to avoid. But so I may just not pursue this too much. But this half could turn into a quarter, a quarter. And that quarter could become an eighth, an eighth. But so what, really? So let me just think about the alternative idea that I was toying with, which was we don't have to make the things go down by a factor of 2 each time. I could start with 1 here, then a half, half. Now, is there some other natural way of making 2 things add up to a half and then 2 things add up to a half that's more natural than... I mean, I'm wondering about Pascal's triangle, that's why I hesitated before. So how about 1 2 1 adds up to 4, but I want the whole thing. I have 1 2, so that would be something like a sixth, a third, a sixth. What is going on there? A sixth plus a third makes a half, and a third plus a sixth makes a half. So I didn't divide by 2 there, but I made that, and I just wrote that because it was sort of natural. I don't think this is going to work though. Or do I? 1, 4, 6, 4, 1. If I take I haven't got there yet. I want 1, 3, 3, 1, don't I? But that adds up to 4, that adds up to 6, and that adds up to 4. And the ratio between a sixth and a third is not 4 to 6. So this Pascal's triangle idea doesn't seem as though it's getting me anywhere. But could it be that that somehow it's nevertheless that there's some better way of doing things than just dividing by 2 at each step? I'm not sure. What about another way? One last thing to try before I just stop, because I've got other things to do. I make this add up to 1, and then this add up to 1 over 2 squared, so I put a quarter, and this has got, no, sorry, it would be an 8 and 8. Then it's gone down when I apply one operation, which is not very nice. So I think I'll scrap that. But I could make it go up a little bit. So instead of 1 half half, what if I went for 1 alpha alpha? I'll be agnostic about what alpha is. Then alpha squared, alpha squared, alpha squared, etc. So if I wanted to make a proof like the one I started with up here work, I would need this not to go down when I apply an operation. I need alpha to be at least a half, but then I'm not better off, so I'll get at least 2 and 3/4. But perhaps I can argue it doesn't go down by too much. So let's just think a little bit about that. So the sum is going to be not terribly nice. The sum beyond this point, I'll have alpha cubed 4 times, and then I'll have alpha to the 4th 5 times, alpha to the 5 6 times, and so on. The sum of, we have that 1 plus alpha squared is 1 over 1 minus alpha. So I get 4 alpha cubed over 1 minus alpha plus alpha to the 4th plus alpha to the 5 plus dot dot dot, all of them over 1 minus alpha, and that's alpha to the 4th times 1 over 1 minus alpha. So I get 4 alpha cubed over 1 minus alpha plus alpha to the 4th over 1 minus alpha squared, which is 4 4 alpha cubed minus 4 alpha to the fourth plus alpha to the fourth, so minus 3 alpha to the fourth over 1 minus alpha squared. Let me just check that if alpha is a half, that's 4 over 8, that's a half minus 3/16 divided by a quarter. In other words, 4 times that, which is 2 minus 3/8, which is not 2 3/4. It's 2 minus 3/4, which is 5/4, which is this, which is what I wanted. And the 2 3/4 came from the initial configuration, but I've got a 1 here now, and I have this number here, which is, if I can show that I've got to get above this number. So after one step I'll have alpha alpha. After another step I've got alpha squared, and after another step something like that, alpha cubed, and then alpha squared. So I don't think that's going to be bigger than this, but I've still got some room to move things. I'm not sure here whether alpha is meant to be bigger than 1 or smaller than 1. Okay, so I'm going to stop here. It doesn't look as though the second part drops out with this particular simplified invariant, but it seemed as though it might do with the one I was looking at in the previous video, and so I'll stop.